Hi, good morning. Okay, cool. Hi, good morning, everyone. So this is going to be the last lecture before exam number 4. So today I'm going to briefly go over what you're going to expect in the final exam. And then first of all, I think I need to go over some important notes. Give me a second. All right, so that's the notes I have for exam 4. So you can find the same thing from the Blackboard. All right. So first of all, I'm gonna post the exam number 4, all the problems on Blackboard at 9 a.m. on Thursday, and then you have 48 hours to solve 4 problems in total. I give you 24 more hours. That's because I tried to solve all the problems by myself yesterday, and it's actually very challenging, I should say, because it's not because the problem is hard. It's just because it involves a lot of calculation. So I think I need to give you more time to allow you to solve all these equations in MATLAB. So I believe 48 hours should be more than enough. So if you have any hard conflicts during that time slot, so you need to email me by the end of Wednesday, so we can hope potentially reschedule for you. So if you don't send me an email and then you didn't get approval by the end of Wednesday, and then you want to late submission once after the exam has been posted, then your final score will be multiplied by 90%. You're not going to get the full points. So any late submission will result in point loss as well. And then if you submit your exam answers like after 6 hours of the deadline, then I'm not gonna grade your answers. So just keep in mind, so that this time that deadline is pretty strict. If you have any conflicts, if you want more flexibility, you need to warn me beforehand. So don't wait for the last minute, okay? Again, 48 hours should be more than enough. The second thing is you directly scan your answers. You can either take pictures or you can use a scanner, but make sure your PDF file is clear. We can read your writings, and then you directly send your answers to Nigel, and then also copy me, okay? And then the third one is that's open notes, open resources. You can use Google, you can use MATLAB, you can use textbook, course notes, whatever resources you can find, so you can use it. But then the only restriction is you have to work on those problems independently. You cannot form a team, you cannot collaborate with each other. So if I notice any suspicious activities, then I reserve the right to ask you additional questions. So when I grade your answers, when I saw, okay, these two answers made the same mistake, I'm gonna like form a team and then ask you individual questions. If you cannot answer my questions, then you're gonna lose points as well. So eventually, to prevent potential collaboration between you, so I try to make each of your exams different. So you're gonna see that some of the problems are related to your student ID. I'm gonna use the last digit, or I'm gonna use the second last digit in some of your exams. So I think you get the point. So there's no it's not going to be helpful if you're trying to form a team. So just try to work on these independently, okay? All right, any questions about these notes? There will be 4 problems in total. I'm going to go over each and every type in this lecture. Okay, so that's the notes. Let me know if you have any questions. Again, if you want another time, if you want more time, if you want late submission, you need to send me an email by the end of Wednesday. All right, so let me see. So these exam 4 is going to cover a lot of things. So that's why you need 48 hours. So the first thing it's going to cover is force analysis. Basically, very, very similar to your homework number 5. So you're going to have I'm going to give you a 4-bar linkage, and then you might have gravity or not. And then you're going to use a motor to drive this 4-bar linkage, and then you need to calculate the driving torque of the motor. And you should be able to use both Newtonian method, and you should also be able to use energy method to find these torque values. So let me see. I think I'm not going to go over these force analysis anymore. I think the lecture notes are pretty clear. And then based on your answers of homework number 5, I think most of you knows how to derive equation of motions using Newtonian method. I think the challenge part for force analysis is how to translate a function from paper to MATLAB. Nigel told me that most of you actually have the correct equations, but then you might have typos here and there when you try to code it up in MATLAB. So I highly recommend you to read my own MATLAB solutions, which is a solution for homework number 5. So if possible, during the exam, you can make minor changes to my code, so you don't have to start from scratch, and then you have less chance to make mistakes. All right, so you're gonna have 2 questions related to force analysis. Let me type it down. 2 questions. So that should be 100 points in total. And then 1 for Newtonian, 1 for energy method. So for the Newtonian, I'm going to ask you to draw a free body diagram and then derive like derive equation of motions for each link. And then you need to find all the equations you need and then organize them in matrix format. And then you need to solve that matrix in MATLAB and then give me the final solution. So the procedures are standard, but it just involves a lot of calculation. You need to be really patient. And then for the energy method, I'm going to ask you like, what's the total energy of the system? What's the kinetic energy? What's the potential energy? And then how much power is generated by external excitations? And then you need to give me the final torque values. So that might include gravity. That might include a spring. That might include a external force, similar to your project number 3. So if you are able to solve homework number 5 and then you understand what's going on my lecture notes, then I don't think you are going to have any problems for these 100 points. So the third one is going to be let me see. 16. Yes. So the third question is going to be about a torque flywheel design. So that one should be simple as it is. So you just need to remember one equation. I'm going to highlight it using red. Oops. That equation is what you need to understand. So IS is the moment of inertia of your flywheel. That's what you want to design. E is the energy variation in your system. K is the fluctuation coefficient. You need to understand what is the meaning of your K. And then omega average is just the average speed or like desired angular speed of your input torque, of your input link. So I think the tricky part is how to find the E, which is the energy variation. So I'm going to briefly review it. So what do you usually do is you have your torque, that is your driving torque or your input torque, that's your theta, and then your torque profile from 0 to 2 pi, that's a full cycle. So did I upload this one? If I don't, then I'm gonna do this. Okay. Is it lecture number 17? Okay, no problem. I'm gonna upload these lectures 17 and 18 on Blackboard right now, after this. Okay, so you have this, you have a driving torque, and then if you remember your previous calculations, your torque is not going to be a constant. It's going to be something like this: zigzag, zigzag, zigzag. And then what you do is you first find the average value. That's your T average. So your T average equals to integration of your T driving torque, which is a function of your theta. And then you integrate it with respect to theta, and then it's from 0 to 2 pi, and then you divide it by 2 pi. So that's how you find your average torque. Okay? So once you find your average torque, then you find these shaded areas. So these shaded areas, oops. All right, thank you. Thank you for a reminder. Yes, they recently added a waiting room system. All right, cool. So once you find it, first step is you use force analysis, find your driving torque of your linkage. The second thing is you use this equation to find the average torque. So once the average torque has been found, then what you do is you calculate the shaded areas using such equation: starting point, ending point, T driving, theta minus T average, d theta. So that's mathematically how you find the shaded area. So let me give you one example. So first of all, you find all the crossing points like A, B, C, D, E, F, and then it goes back to A. A, B, C, D, E, F, G, or G is actually A because after one cycle it repeats. So you find all these crossing points. So what you do is you calculate the shaded area between two crossing points. For example, between A and B, your shaded area, let's name this as area E1. Your E1 is integration from A to B, and then T driving torque minus T, oops. So mathematically, that's how you find area enclosed by two curves. So that's your curve number 1. That's your curve number 2. If you want to find the area enclosed by 2 curves, that's how you do it mathematically using calculus. And then you find the E1. In the same way, you can find the second area, E2. In this case, you're integrating between B and C, and then you have your E3, E4, E5, oops, and E6. So in the example, you only have 4 areas, but in here we have 6. And then exam, you might see less or more. So what you do is after that, you organize them column-wise. E1, E2, all the way to E6, and then you have to label them like what this energy is about. That's between A and B. That's between B and C. The last one is between F to G or A, right? So I think I post a scanned PDF on Blackboard. So that's actually from the textbook. So what the textbook is doing is you first create a table, something like this. The first column shows how you get your shaded area. Where are those crossing points? The second column is what are the values of those shaded areas. And then the last one is accumulated summation. So the first one is just E1. The second one is E1 plus E2. And then the third one is E1 plus E2 plus E3. And then the very last one is just E1 plus E2 plus E3, all the way to E6. So you calculate these accumulated sum. Make sense? And then once you find these accumulated sum, then you find the maximum and minimum summation. So it's not very clear here, but when you go back to example 1, you have a better understanding. So in your example 1, we only have 4 shaded areas. Let me see. Okay, so what do we do is you first find your A. You find a point A, you find a point B, and then you find a C and D, and then eventually goes back to A. So these 5 crossing points divides your total torque into 4 sessions. So for each session, you calculate the area, and then this area is your shaded areas, is your energy. So you lay out all these 4 energies column-wise, okay, as shown in here. So you lay out them column-wise, and then you also want to point it out what this shaded area is about. For example, the 200.73, that's your first area, is between point A and B. So you need to label out that is from A to B. So once you have all of this, you just do the summation as I mentioned before. And then once you have all these summations, you want to find the maximum and minimum number. And then the difference between the maximum and minimum is going to be the E you're going to use in this equation. Where is it? Okay, you remember that very first equation I mentioned, right? This equation. So that's the equation I mentioned. So in order to find this E value, this E value is the difference between, basically the range. So you use the maximum value minus the minimum value. So that range is going to be your E. And then the other thing is, as I said, when you design a flywheel, you're actually sacrificing the constant speed input assumption. So if you have a flywheel in your system, so then your input speed is no longer constant. So that means your theta dot is going to be varying. So how can you find, so that means your theta 2 dot is changing, is fluctuating. So the variable k describes how much your velocity is fluctuating. So that's called fluctuation coefficient. The other thing is, how can you find at which point your theta 2 dot reaches maximum? Okay, so in this case, you find where your energy, where your accumulated summation has a minimal value. So that means here, after B to C, which means at crossing point C, your energy is minimum. If your energy is minimum, this energy means how much energy your system needs to drive the entire linkage. So you can assume that your motor is inputting a constant energy. So there is a constant energy input from motor. You can assume this is constant. And then these E, which is 1, 2, 3, 4 numbers. So these numbers, they are the energy we needed to drive the system, actual energy we needed. So in this case, I should put it in a different way. Actually, these 1, 2, 3, 4, they are the energy saved by the system. So that means here in step 1, it actually needs 200.73 more energy to drive the system. And then in the step number 2, your system actually saves 60 energy. So that means most of the energy is not used. So if that's the case, that means in here we have more than enough energy. If that's the case, then that means your system is going to rotate much faster. Okay, so in other words, that means at point C, when you have the minimal energy, when you have a negative term, that at point C, your theta 2 is actually maximized. So in other words, in order to find, so that means when you follow this line, follow the line of the torque. So your input theta 2 dot is actually varying. So that means at each different point, your theta 2 dot is actually changing. So what if you want to find the maximum velocity? So what you do is you go back to the table. You go back to this table, and then you find your last column, which is the accumulated sum. And then you find the last column, the accumulated sum, and then you find the minimal value in that column. In this case, that's the second row. Once you find the minimum value, then you go back to the first column and then find out which point, well, where is the ending crossing point. In this case, the second column means your system ends at point C. So this point C is going to give you the maximum rotating speed. You can do the same thing to find out the minimum rotation speed. So if your rotating speed reaches a minimum value, that means your mechanism is actually asking for more energy. So that means you need to find the maximum value. Oops. You need to find the maximum value in the last column. And then the maximum is the first row in this case. And then it requires 200 joule or more energy. So that means because your system is asking for that much energy, so but it cannot get it. So the only thing it can do is just reduce the speed. So the more energy it asks for, the more speed is going to reduce. So that means from A to B, your system is actually reducing speed. And then the speed reduction reaches maximum at point B. So that means at point B, you have the minimum theta 2 dot. All right. So any questions about these flywheel design? What did I just calculate? So in flywheel design, I'm going to ask you two things. Okay. So the first thing is I'm going to ask you to design a flywheel. You need to find these IS values, which is a moment of inertia of your flywheel. Then you need to find your E, K, and omega average. Okay. The second question I'm going to ask you is, as your torque is varying, if you look at these torque, as your theta 2 is rotating, actually the velocity is not constant anymore because of the flywheel. So that means your input velocity theta 2 dot is varying. The second question I'm going to ask you is, at which point you get the maximum theta 2 dot, and then at which point you get the minimum theta 2 dot. So in order to find the maximum input speed and minimum input speed, you have to go back to your table again. You need to find the minimum and maximum value for the last column, which is accumulated energy. And then the ending point for the minimum energy is going to be the maximum speed. And then the ending point for the maximum energy is going to give you the minimal speed. Yes, I might not give them directly to you. You need to understand the physical meaning of K and T average. I remember last year. I can give an example. What are you expecting? Last year, I'm gonna. Oops. Last year, I gave a student a sine wave with a constant shift. So your T torque is A sine T plus B. Then you need to find your average torque by yourself. Well, so by definition, I'm going to briefly introduce your K. K is your omega maximum minus omega minimum over omega average. That's by definition. That's the definition of fluctuation coefficient. Yes, Matt, you're correct. In this case, your average torque is directly B. All right. So that's for flywheel analysis design, I believe that question is, I think that question is 40 points. I think that's easiest 40 points is gonna have in this class. Okay, so chem design, gosh, that's 60 points. I'm expecting, I think the chem design is gonna be the most difficult one for you. So here, I'm gonna go over homework number 6 briefly. So this is due tomorrow, and I'm gonna post the solution online right after tomorrow at noon. So you might want to check my solutions. So if you're able to solve your homework 6, then you would have no problem with your finals. If you have any questions related to homework 6, please let me know before Thursday. And I think you need to figure out how to solve homework 6. All right. So, all right. So again, when you design a chem follower, actually, what do you CPM for? The initial conditions, yes, they're going to be really similar. And then considering the CPM and CPE, or CPM, or what's the other one? Critical path motion and critical extreme position, CEP, I believe. So CPM and CEP, there's no strict difference. They're actually very similar. You can consider CEP is a special case for CPM, right? Because for CPM, you're designing displacement, velocity, acceleration. But then for CEP, you only design for displacement. So it's simpler, but actually you have the same concept. You're going to have similar initial conditions. So all your angles will be in radian. They're not going to be in degrees, but then that's just a minor difference. And I'm not sure about the similar initial conditions. You're going to expect some minor changes, but overall they should be really similar. So you might, so here in this case, we're accelerating and then maintain a constant speed and then deaccelerate. I might deaccelerate first and then increase your speed in a constant rate, which means your acceleration is constant, and then it go back to the original position. So I can play like millions of tricks to get different like segments for you, but the concept will be very similar. So the first thing is, usually the first step, so for the CPM design, I'm gonna give you the width of the segments in time domain. So here, we know that the total cycle time is 4 seconds. And then these 4 seconds, because that's one cycle, that corresponds to 2 pi. And then these 4 seconds is divided into 0.5, 2, and 1.5, right? And then we know that the entire span of this range is 2 pi. Then you can easily give, let's see, that's half pi. Wait, that's 4. Okay, wrong. So this width is 1/4 of a pi, 3/4 of a pi, and then that should be pi. So whenever you see a CPM, the first step is you need to translate all the time domain information to theta domain, because all your design is done in theta domain. If it's CEP, then everything is provided in theta domain directly, so you don't have to worry about anything. Okay, so you have all of this. So you know that, okay, that's your S theta. That's your theta. And then you know that you can divide your theta domain into 3 sections. There's 0, quarter of pi, 1/4 of a pi, and then 2 pi, because you know the width. All right. Once you know the width, you can find the starting and ending point for each segment. So that's your S theta. You just repeat the same thing. That's your velocity diagram. And that's your acceleration diagram. So you first divide all these diagrams into the segments we want. And then the second thing is, let's find out what we already know based on these problem description. So in this case, I don't give you an initial position. You can either assume theta equal to 0. That's the initial position. Okay. In the exam, there won't be any confusions. I try to be very, very specific. I already give you the initial position. So here we know that this is initial position. And your system first accelerates from 0 to 300 millimeters per second. So it starts from here and then it accelerates. So it ends at some point in here. But then what is this number? Let's name it as V naught. Is it 300? Yes, that's the most important thing. You cannot directly copy this velocity here. Remember, your V theta by definition is ds theta d theta. So the unit for your S is millimeter, is a length, is a unit of length. Your theta is radian. So eventually your unit is in millimeter per radian. But then your velocity here is in millimeter per second. So that means you cannot directly translate your velocities. So that's the first part you have to pay attention to. So you have to first convert your time domain velocity to theta domain. Let me see. Remember the triangle I provide you during the lecture 20? So you have to keep that triangle in mind, how to dump information between different domains. So if you forget, I'm going to write it down. So your V theta is going to be, oops, Vt over theta dot. Okay. Yeah, Rob. Yes, you're correct. So the unit for the y-axis will be meters per radian or meters per radian square. And it doesn't have to meters. So depending on what unit you choose for your length. In this case, if we choose millimeters for the S diagram, then this is going to be millimeter per radian and millimeter per radian square. If you choose meters for S, then everything becomes meters. So just keep consistency, will be fine. All right, so let's go back to these relationship. You have your Vt over theta dot, and then what is your Vt? Is 300. Your theta dot is 90 degrees per second. So let's translate it to radian. That's half pi radian per second. So you divide it by half pi, and then 600 over pi. So that means your V naught should be 600 over pi. All right, so we know that it starts from 0, it ends at 600 over pi. That's from the step number 1. So in the second segment, it says it maintains constant speed at 300 millimeters per second for 2 seconds. So we know that the speed is going to be constant. You don't have to calculate the constant speed again because you should start from 600 over pi. All right. If the speed is constant, what do you know about the acceleration? It should be 0, right? And then your displacement would be a linear line with a constant slope. The slope is going to be your velocity. All right. So the last step is it returns back to the starting point. So that means your displacement returns to the back starting point. And then because we know your velocity starts from 0, and then your S, V, and A should be continuous. So that means your velocity should also be 0, right? One thing you have to pay attention is your S, V, and A, they should be continuous. They should be continuous. So by reading the problem description, that's all we can get. So you cannot say that your acceleration is initially 0 because the problem doesn't say that. I believe you can still solve the problem, but then your problem would be over constrained. Well, that's a tricky question. I'm gonna explain this to you. So depending on where you start your design, if you start your design in segment 3, then segment 3 has 5 boundary conditions. If you start your design in other segments, then it's really hard to tell. Okay, so that's why I think the CAM design is very tricky. So to help me to easily grade your homeworks, so let's always start with segment 1, okay? So in your homeworks, let's start from segment number 1. You can definitely start with your segment number 3. I'm gonna explain this to you later. So if you start with segment number 1, so what you do is you just focus on what you already know, all the boundary conditions. Oops, what happened? All right. So you know all the boundary conditions in theta domain when theta equal to theta naught. Oh, the first thing is you find the starting point theta naught, you find the ending point theta 1, and then you calculate the range of your theta in that segment. And then you write down all the boundary conditions you have for segment number 1. That's 0. And as theta equal to theta 1, that's something we don't know, question mark. Oops. So V theta equal to theta naught, that's 0. V theta to theta 1, that's 600 over pi. And then A theta equal to theta naught, that's something we don't know. And then A theta to theta 1, that's 0. So if you don't know how to write down your boundary conditions, you just lay out all the 6 possible boundary conditions. If you don't know it, put a question mark there, okay? So 1, 2, 3, 4, we have 4 known boundary conditions. Then what we do, we assume that your Sx is C0 plus C1x plus C2x plus C3x squared. So because we have 4 equations available from boundary conditions, so you have 1, 2, 3, 4 unknowns in the polynomial. And then if you have your SX, then you have your VX, you have your AX. That's C1 plus 2C2X plus 3C3X squared. That's 2C2 plus 6C3X. Usually I will align my C2 and C3s, so you have less chances to make a mistake. So your polynomial is in X domain. Your equations are in theta domain. So then we need to translate all your theta domain information to X domain, right? What do? Is you go back to your triangle and then find out the your Vx is beta V theta. Your Ax is beta square A theta. That's how you dump information between different domains. Then let's write down. You have your S, X. Oh, one thing you might forget. So X is theta minus theta naught over beta. So that's a linear transformation. So your Sx equal to 0. That's 0. Sx equal to 1 is a question mark. So again, all the information in displacement domain can in S domain, in S can be transferred directly. Your Vx equal to 0. That's 0. Your Vx equal to 1. That's beta square. That's beta, which is 4 pi times 600 pi over pi. That's 150. And then you have your Ax equal to 0. That's a question mark. You have Ax equal to 1. That's 0. So then you can solve these equations. I forgot what the solution is. Let me see. Okay. So I believe eventually your Sx is 150 x squared minus 50 x cubic. So then you find a polynomial in X domain, but you cannot just end it there. Because as I said, in order to find your cam design, you need to find your S theta. So that's why eventually you need to use this relationship. You need to use this equation to translate your X. Oops. To theta. So your S theta will be 150 theta minus theta naught is 0 over pi over 4 minus 50 theta minus 0 pi over 4 cubic. And then that is your S theta. The second thing is your S theta is actually only available in the segment number 1, right? So that means your theta has a range. It's from 0 to a quarter of pi. So that should be the final solution for your segment number 1. Yes, you can do that, but well, then things become tricky. Then you have to use a chain rule. I won't recommend that. So you're more likely to make a mistake. So what I would suggest you to do is, if you want to find your V theta and A theta, I would recommend you to start from your S theta and then do derivatives. That's the best way to do it. You can go back and check my lecture 20 notes. Last night I posted the MATLAB file on Blackboard under the lecture 20. So that lecture 20 MATLAB live script code has all the information you need to find the V theta and the A theta. So that's one way to do it. you can actually translate your Vx to V theta as well. But then it's not that straightforward. You use MATLAB. So in the exam number 4, the final exam, I'm going to ask you to plot SVAJ. So what you do is you can create your plots in MATLAB, and then you can just take a snapshot. You can print the screen, take a clear snapshot, and then post that to a PDF file. If you don't know how to do it, you can. There are a few ways to do it. You can Google merge PDF. You can save your snapshot to a PDF file, and then you can merge multiple PDF files together. Just Google it. There are a lot of like free online tools. So this method is recommended. This method is also okay, but then it's just trickier. For example, your dv theta, because your your Vx is dVx. Oh, sorry. Is dsx over dx, and then your V theta is ds theta over d theta. You can see that the transformation is not straightforward. You need to use a chain rule, but it's doable. It won't be as easy as the first method. Okay. So that's how you find S, V, A, and J. Oh, I forget J. J theta is just one more time derivative. Oh, sorry, theta derivative. All right. So that's how you find your SVAJ for segment number 1. So the second thing is, actually, your segment number 1 design is not completed yet, because we still have 2 question marks. So you need to complete these question marks before you move to the next segment. Okay. So let's see. So these are the 2 question marks. So what you can do is, because right now you already have the S, V, and A and J as a function of theta, you just plug your theta 1 and theta 0 back into these functions, and then you can get this value and this value. So in other words, once you finish design your polynomial for one segment, that means all 6 boundary conditions are already known. So for example, here we have 2 question marks. At the beginning, we don't know what they are. But after designing segment number 1, you already know these points. You already know these points, those black points. And considering that your system is continuous, so if it starts from this point, then the ending point will be at the same location. All right. So then you can move on to the segment number 2. So then we put a conclusion for segment number 1, and then segment number 2. So actually in your CPM, there are 2 types of designs. The first type is when you know boundary conditions. So basically that's your segment number 1, right? You have nothing, you know nothing about what's happening in between 2 points, but then you do know what's happening at those starting points and ending points. So those are the boundary conditions. What do you mean? To find which coefficients? Do you mean to find the C1, C2, and C3? Yes. So your Sx, Vx, Ax. So when your V is a function of your x, that by definition your Vx is dsx dx. So that means all the derivatives are with respect to x. So this is actually dsx dx, second derivative. So that means your S, V, and Ax, they're all in x domain. So, but in order to solve these equations, your equations should be written in x domain as well. So that's why your SVA in x should be solved by your SVAJ in x domain should be solved by all these equations in x domain. Once you solve your coefficients in x domain, then you already know your Sx, right? Your X is here. Then you can directly replace your X by theta. Then you get your solution in theta domain. At that point, that's actually a good question. So the other way to do it is, okay. So here you can see 3 different blocks. Hopefully that's clear enough. I'm gonna use a different color, green. So you have your equations in x domain. So sorry, you have the polynomial in x domain. You have your equations in x domain. So what we do is you dump all the theta domain equations to x domain and then solve everything in x domain and then transfer it back to theta. If you don't want to do it in that way, you can actually do it the opposite. You can first plug your s theta back in. So then that's all your equations in theta domain. And then you can directly use the theta domain equations. That can give you the same coefficients as well. But then just make sure your polynomial assumption and your equations are in the same domain. You see what I mean? You can either use the green boxes or use the red boxes to find your C coefficients. But you cannot pick one from green, one from the red to find your coefficients. No. So I think your question is, okay, let me write it down. I think I understand your question. Let me copy this. Oops. Copy. So that's our Sx, right? And then that's our Vx is going to be 300x minus 150x squared. So I think your question is, can we directly get V theta by replacing x equal to theta minus theta naught over beta? Is that a question? The answer is no, you cannot do that. Let's try it out, then you can see why. And your V theta by this case is 300 theta minus theta naught over beta minus 150 theta minus theta naught beta. So if we directly replace your theta x by theta, then that's what we got. And then you can copy. Okay. So if we do it in the correct way, you first translate your Sx to S theta. your S theta would be 150 theta minus theta naught over beta square minus 50 theta minus theta naught beta square. And then by definition, your phi theta should be ds theta d theta, right? So that should be beta times 150 theta minus theta naught. Oops. So you're missing that 1 over beta coefficient. To explain this, you need to go back to the chain rule here. Because ds dx, that's your vx. So that means eventually that equals to vx times dx d theta. So that is where the 1 over beta come from. All right, so that's how you calculate SV and A and J. So my suggestion is doing all the trick for S theta only. And then when you're trying to find your V theta, A theta, just go back to the definition. If you scroll down more, Vx. Yeah, Cody, I think you're correct. Yes. If you go back to the triangle, then that's okay. Yes. If you go back to the triangle, then the beta has been taken care of. Then you're gonna get the correct answer. So I'm emphasizing that. So you can do all. So you can pick the method you like the most, but then just be careful. Which boundary condition does C3 come from? I'm not sure if I understand the question. So are you saying how we find the C3 coefficient? Okay, so right now, let me write it down. Before moving to segment number 2. Cut. Oops. All right, so let me keep talking about these for a minute. So here you have 1, 2, 3, 4 equations, right? So let's find it out. We know that when x equal to 0, your equation should be 0. So that means the first equation is s x equal to 0. You know that your x here, you go back to these equations, okay? And then when x equal to 0, you have c0 plus c1 times 0 plus c2 times 0 plus c3 times 0 that equal to c0. That gives you 0. And then s, the second equation is about v. Vx equal to 0. You can use the same method, plug 0 back into Vx. Then you only have C1 left. That's 0. And then you have x equal to 1. Then you have C1 plus 2C2 plus 3C3. That's 150. And then you have Ax equal to 1. That's C2 plus 6C3. That's 0. So you have 4 equations here, right? You have, let me circle out all the unknowns. 1, 2, 3, 4 unknowns, 4 equations. Then you can solve them. So there are a few ways to solve it. You can either use MATLAB, or you can, in this case, because it's so easy, you can just calculate it by hand. But then if you do see more equations and more complicated combinations, then I suggest you to use MATLAB. All right, so that's for segment number 1. Let me number. So segment number 2. So segment number one is when you know all the boundary conditions. You've known nothing about what's in between. So what you do is you just assume that between those boundary conditions, there is a polynomial. That's how you do it. But in segment number two, that's different. If you go back to the original plot, for these segments, we already know what's happening in the entire segment. So you cannot assume a polynomial anymore. You already know the shape of the function, right? So there are a few ways you can start with. So you know that your v theta is a constant equals to 600 over pi, I believe. Oh, again, I would suggest you to write the starting point, find the ending point, and then find the beta, which the width. At the beginning of your design, just write down all these three numbers. Keep this in mind, and then you won't make any mistakes. If you forget to calculate these, you might accidentally use the beta from the previous step, and then you have a wrong solution. All right, so you have all of this, you have v theta, and then we know that your v theta is a constant. Then by definition, your s theta is just the integration of v theta, right? And then that's going to give you 600 over pi times theta plus k. This is a constant. This is TBD, to be determined. But then the good news is we already know the boundary conditions, right? We already know these black points because we already know that black point because that black point has been calculated here. Because once you calculate your s theta, then you already know the black point. I forgot what that is. Let me calculate it out. Let me copy all of this here. Oops. What did I do? Copy. Okay, so that's from the first segment. So we already know that your s theta equal to 4 pi. If you plug back in, that's 100 minus 50. That's 100, right? So we already know that when theta equal to 4 a quarter pi, that's going to be 100. So here we already know that your s theta, in this case, your theta is from quarter pi to 5/4 pi. But then these s theta should connect with your previous s theta because of the continuous assumption. So that's why your 600 over pi when theta equal to a quarter pi plus k, that should give you 100 as well. So that gives you k equal to minus 50. So in total, your s theta would be 600 pi theta minus 50. And then that is only true when your theta is in the second segment. When you know everything about one segment, then the design becomes really easy because you already know the entire function of that segment. You might only have one or two constants to be determined from the boundary condition. Make sense? So in this case, I'm giving you a constant velocity. You might want to think about what if I give you a constant jerk? What if I give you a constant acceleration? If I give you the constant acceleration, then you have two coefficients to be determined, right? If I give you a constant jerk, then you have 3 coefficients to be determined. But then the method is the same. Can you show EX? What is EX? I don't understand. Or example. Okay. All right. So let's see. In this case, that might be really hard to get. Okay. So if I assume that your segment, let's assume, I'm changing the problem here. If it's not constant velocity, assume your J theta is constant. Okay. Let's say that J theta has a constant of B. Then your J theta is B. That's going to give you your A theta, right? And then that's going to give you V theta. That's going to give you S theta. So in this case, you're going to have 1, 2, and 3 unknowns to be determined. Then you need to go back to your boundary conditions. Hopefully you can find 3 equations to solve for all these boundary conditions. Make sense? So that's when jerk is constant. You can also assume when velocity acceleration is constant, then you're only getting 2 unknowns, right? But then you can still solve them from boundary conditions. All right, that's just something like a bonus. It's not related to the homework 6. So just make sure you don't get confused. All right, so once you get your S theta, as I said, it's not done yet. Okay, you have to go back to your segment because here you also have 1 black point that needs to be defined. You need to find where your S theta equals to 5/4 pi is. If it's 5/4 pi, then it's 600 over 4 pi 5 pi minus 50. How much is it? Oh gosh. 0.5, 50. Is it 700? Okay, cool. All right, so then you know the black point is 700. And then that actually goes back to the very first question somebody asked me. Yeah, Andrew. So that goes back to your question. So right now you see that as we complete other segments, you're getting more boundary conditions. So once we finish segment 1, segment 2, the last segment you're actually have 6 boundary conditions. It all depends on where you start your design. If you start your design at segment number 3, we know nothing about those black points. So you actually have 4 boundary conditions for segment 3. But then if you leave your segment number 3 in the end, then we already have all the information. So you have 6 boundary conditions. But to make my own life easier, please start your design in the first segment. All right, so that's for CAM design. And then in the end, as I said, you need to, so you can do your segment 3 after this. I'm going to post the solution on Wednesday. And then, as I said, eventually your S theta would be a piecewise function. It's going to be 150 theta over pi 4. Minus 50. And then you have this, and then this is theta between quarter pi to 5/4 pi, theta from 0 to 4/4, 1/4 pi, and then in the end. So you have these piecewise function. You can use MATLAB to plot these piecewise function. And then when you check your SVAJ, your SV and A plots should be continuous. You shouldn't see any discontinuity in your plot. If you do see that, then something is wrong with your calculation. All right, so that should be it. All right. Yeah, let me know. As I said, if you do need more time, just send me an email.